Okay, um, this podcast is going to deal with muscle tissue. We're going to talk about the three types of muscle tissue, where they're found, and what they look like. We'll talk about the structure of a whole muscle, all the way down to the structure of a muscle fiber and a myofibril. We'll talk about how muscles contract at the molecular level. We'll talk about the role of calcium and ATP in contraction, and describe the relationship between skeletal muscles and nerves, talk about motor units and their relationship to recruitment, and the events that occur at the neuromuscular junction. Okay? So first what we want to do is we want to talk about muscle tissue in general.
Muscle tissue is widely distributed throughout the body. The primary function of muscle tissue is to produce movement of the skeleton or other tissues of the body. This results in body or organ movement, maintenance of posture, communication such as facial expressions and vocalization, control of body openings, and heat production. Muscle tissue is composed of cells called muscle fibers. Each fiber contains contractile proteins that contribute to the properties of muscle tissue. These include excitability, conductivity, contractility, elasticity, and extensibility. There are three types of muscle tissue: skeletal, cardiac, and smooth. Skeletal muscle is under voluntary control and is usually attached to bones via tendons or other connective tissues. Skeletal muscle fibers, or cells, are long, thin, and cylindrical. Each fiber has multiple oval-shaped nuclei located just deep to the sarcolemma, the plasma membrane of the muscle cell. Skeletal muscle fibers are surrounded by a delicate layer of connective tissue called the endomysium. Multiple muscle fibers are bundled together to form fascicles, which are covered by a dense connective tissue layer called the perimysium. The perimysium contains the nerves and blood vessels that supply the muscle fibers. Numerous fascicles are then collected to form a muscle that is covered by an external sheath of dense connective tissue known as the epimysium. The cytoplasm of a skeletal muscle fiber is called sarcoplasm. The sarcoplasm of a muscle fiber contains long cylindrical structures called myofibrils. Each myofibril is composed of bundles of short myofilaments. There are two types of myofilaments: thin filaments, which are composed primarily of the proteins actin, tropomyosin, and troponin, and thick filaments, which are formed by the protein myosin. The two types of myofilaments are arranged in parallel, and when viewed along their long axis, they exhibit alternating dark and light bands known as striations. The dark bands, called A bands, represent the entire length of the thick filament. Conversely, the light bands, called I bands, represent thin filaments only. The Z discs, dark transverse bands at the center of the I bands, represent fibrous protein structures composed of connectin, to which the thin filaments are anchored. The sarcomere is the functional contractile unit of skeletal muscle. It is defined as the region within a myofibril between adjacent Z discs. There are numerous sarcomeres in each myofibril. Cardiac muscle is found only in the walls of the heart and is under involuntary control. Cardiac muscle fibers are short branch cells with one or two centrally located nuclei and numerous mitochondria. These fibers exhibit striations and banding patterns similar to those seen in skeletal muscle fibers. Cell junctions, called intercalated discs, are unique to cardiac muscle. Two specializations within these junctions link cardiac muscle fibers both electrically and mechanically. Gap junctions form an electrical connection by allowing ions to flow from cell to cell, facilitating the spread of impulses that enable cardiac muscle to contract as a unit. Desmosomes contribute to intercalated discs as mechanical junctions that prevent cardiac muscle fibers from pulling apart during contraction. Smooth muscle is located in the wall of blood vessels, ducts, and organs, and is under involuntary control. Smooth muscle cells are elongated, with tapered ends, fusiform-shaped, and contain a single, centrally located nucleus. The myofilaments are not arranged in any specific pattern, and, therefore, do not produce visible striations or form sarcomeres. Instead of the Z-discs present in skeletal and cardiac muscle, smooth muscle contains dense bodies that serve as attachment sites for thin filaments. Dense bodies are small protein concentrations distributed throughout the cytoplasm. Typically, smooth muscle cells are tightly packed and arranged in sheets. Their contraction is slow and resistant to fatigue. Like cardiac muscle, some smooth muscle fibers contain gap junctions that spread electrical impulses and allow smooth muscle to contract as a coordinated unit.
Now, notice that muscle is considered an organ. A muscle is considered an organ because it contains a blood supply, it contains connective and muscle tissue, it contains a nerve supply, and is also attached to bone by structures that are called tendons. The connective tissue that holds muscle together wraps around each individual cell and is known as endomysium. Bundles of these enclosed cells, called fascicles, are enclosed by paramysium, and bundles of these fascicles are enclosed by connective tissue called epimysium. The epimysium is continuous with the tendon, which is continuous with the periosteum, and that's how we're able to affect movement, right? When the muscle contracts, the two attachment points of the muscle, the origin and the insertion, move closer to each other. The insertion, in this illustration, which would be down here on the forearm, okay, is the movable part of the action, and the origin is the part that doesn't move, okay? So this movement of the contraction of this muscle, which is called the biceps brachii, would be classified as forearm or elbow flexion, because we're decreasing the angle between two components from anatomical position. You remember anatomical position as standing with feet flat on the ground, facing forward, and your palms facing forward, okay? And then everything is related to that. Remember that muscles can form attachments to other structures in three ways. The tendon can attach the muscle to the bone, as we've already indicated. The muscle can also attach directly without a tendon to bone or soft tissue. And you can also attach to a sheet-like tendon, which is called an aponeurosis. And you see this on the top of the cranium, and you also see it running down the midline of the abdomen, okay? What we're going to look at now is the sequence of events that ultimately leads to skeletal muscle contraction.
Nerve impulses, also known as action potentials, travel from the brain or spinal cord to trigger the contraction of skeletal muscles. An action potential propagates down a motor neuron to a skeletal muscle fiber. The site where a motor neuron excites a skeletal muscle fiber is called the neuromuscular junction. This junction is a chemical synapse consisting of the points of contact between the axon terminals of a motor neuron and the motor end plate of a skeletal muscle fiber. The events at the neuromuscular junction occur in 7 coordinated steps. Step 1. An action potential travels the length of the axon of a motor neuron to an axon terminal. Step 2. Voltage-gated calcium channels open and calcium ions diffuse into the terminal. Step 3. Calcium entry causes synaptic vesicles to release acetylcholine via exocytosis. Step 4. Acetylcholine diffuses across the synaptic cleft and binds to acetylcholine receptors, which contain ligand-gated cation channels. Step 5. These ligand-gated cation channels open. Step 6. Sodium ions, shown here in red, enter the muscle fiber, and potassium ions, shown here in blue, exit the muscle fiber. The greater inward flux of sodium ions relative to the outward flux of potassium ions causes the membrane potential to become less negative. Step 7. Once the membrane potential reaches a threshold value, an action potential propagates along the sarcolemma. Neural transmission to a muscle fiber ceases when acetylcholine is removed from the synaptic cleft. This removal occurs in two ways. 1. Acetylcholine diffuses away from the synapse. 2. Acetylcholine is broken down by the enzyme acetylcholinesterase to acetic acid and choline. Choline is then transported into the axon terminal for the resynthesis of acetylcholine. Typically, a single motor neuron arising in the brain or spinal cord conducts action potentials that travel to hundreds of skeletal muscle fibers within a muscle. The sequence of events that converts action potentials in a muscle fiber to a contraction is known as excitation-contraction coupling. If we look at a single muscle fiber, we see that an action potential travels across the entire sarcolemma and is rapidly conducted into the interior of the muscle fiber by structures called transverse tubules. Transverse, or T-tubules, are regularly spaced enfoldings of the sarcolemma that branch extensively throughout the muscle fiber. At numerous junctions, the T-tubules make contact with the calcium-storing membranous network known as a sarcoplasmic reticulum, or SR. Where it abuts the T-tubule, the SR forms sac-like bulges called terminal cisternae. One portion of a T-tubule plus two adjacent terminal cisternae is known as a triad. The membranes of the T-tubule and terminal cisternae are linked by a series of proteins that control calcium release. As an action potential travels down the T-tubule, it causes a voltage-sensitive protein to change shape. This shape change opens a calcium release channel in the SR, allowing calcium ions to flood the sarcoplasm. This rapid influx of calcium triggers a contraction of the skeletal muscle fiber. Thus, calcium ions are responsible for the coupling of excitation to the contraction of skeletal muscle fibers. The contraction of a skeletal muscle generates the force necessary to move the skeleton. A contraction is triggered by a series of molecular events known as the cross-bridge cycle. In a skeletal muscle fiber, The functional unit of contraction is called the sarcomere. A sarcomere shortens when myosin heads in thick myofilaments form cross bridges with actin molecules in thin myofilaments. The formation of a cross bridge is initiated when calcium ions, released from the sarcoplasmic reticulum, bind to troponin. This binding causes troponin to change shape. Tropomyosin moves away from the myosin-binding sites on actin, allowing the myosin head to bind actin and form a cross bridge. Also note that the myosin head must be activated before a cross-bridge cycle can begin. This occurs when ATP binds to the myosin head and is hydrolyzed to ADP and inorganic phosphate. The energy liberated from the hydrolysis of ATP activates the myosin head, forcing it into the cocked position. A cross-bridge cycle may be divided into 4 steps. Step 1. Cross-bridge formation. The activated myosin head binds to actin, forming a cross bridge. Inorganic phosphate is released, and the bond between myosin and actin becomes stronger. Step 2. The power stroke. ADP is released and the activated myosin head pivots, sliding the thin myofilament toward the center of the sarcomere. Step 3. Cross-bridge detachment. When another ATP binds to the myosin head, the link between the myosin head and actin weakens, and the myosin head detaches. Step 4. Reactivation of the myosin head. ATP is hydrolyzed to ADP and inorganic phosphate. The energy released during hydrolysis reactivates the myosin head, returning it to the cocked position. As long as the binding sites on actin remain exposed, the cross-bridge cycle will repeat. And as the cycle repeats, the thin myofilaments are pulled toward each other and the sarcomere shortens. This shortening causes the whole muscle to contract. Cross-bridge cycling ends when calcium ions are actively transported back into the sarcoplasmic reticulum. Troponin returns to its original shape, allowing tropomyosin to glide over and cover the myosin-binding site on actin.
Okay, couple things to note are that the events that happen at the neuromuscular junction can be interfered with in a variety of ways, right? If we damage the motor neuron, we won't get the chance to cause release of neurotransmitter at the neuromuscular junction, and the result will then be no change in the voltage across um, the membrane of the muscle cell that would lead to an action potential, and the result would be no movement. Okay. There are drugs, for instance, that can block this. Okay. Another example of a condition that affects the neuromuscular junction is myasthenia gravis, and this is caused by damaged receptor sites on the muscle membrane. The receptor sites are altered so that they can't effectively bind acetylcholine. The way this happens is that the immune system generates antibodies that actually block the acetylcholine receptors. And so when the acetylcholine is released at the neuromuscular junction, it has nowhere to bind, and we don't open any sodium gates, and the result is that we don't get any change in voltage and thus no action potential. Curare works by blocking receptor sites on the muscle membrane, because the receptors are occupied by the drug, acetylcholine can't bind the receptor site, and muscle contraction doesn't happen. Okay, so this is, in a way, similar to the effect that myasthenia gravis has. And then there are neurotoxins. Okay, Clostridium tetani and botulinum have effects on the neuromuscular junction as well. Um, Clostridium botulinum is going to prevent muscle contraction, while Clostridium tetani is going to cause the muscle to remain in what we know as a sustained contraction. Okay, and that's typically called tetanus. Okay, so these are two types of bacteria that like to grow in anaerobic conditions, low oxygen conditions, and these are their defense mechanisms in order to prevent them from being destroyed. Right? You know, botulism toxin better as Botox. This is one of the ways that they reduce wrinkles. It's a temporary condition that Botox eventually loses its potency and the wrinkles will return. Tetanus from Clostridium tetani is a dangerous condition because if we don't give you tetanus antitoxin, we can eventually go into a tetanic contraction at the diaphragm and at the heart, and the result can be death. Okay. Now, motor unit is defined as a motor neuron and all of the muscle fibers that it talks to. And this is one of the ways that we can generate more power out of a muscle contraction when the load on the muscle increases, is that we can utilize more motor units in the activity and generate more power because more fibers would be participating. Another way that we can do this is by varying the frequency of action potentials on a single muscle fiber. The more rapidly action potentials are set to a single neuromuscular junction, the less opportunity there is for calcium to be recovered by the sarcoplasmic reticulum. And the result is that with the next action potential, more cross bridges are formed and more power is generated. Okay, so this will follow a succession from a simple twitch, which would be a single action potential, and that's very rare in normal movement, to a volley of action potentials that produces what we call treppy, and that's a stair-step effect in the production of tension with each successive action potential. And then when we increase the frequency of action potentials even greater, we get something called unfused tetanus, where you have periods of tension and relaxation that sort of oscillate around a peak. Okay, and then very rarely we'll see something called fused tetanus, in which there is no period of relaxation at all in the muscle fiber, and the result of that eventually is that the muscle will be exhausted out of energy. Okay, because that's the maximum amount of energy expenditure a muscle can engage in. Okay, we're going to talk about muscle contraction, talk about twitch and tetanus, and ID where the energy comes from in muscle contraction. Talk about the sequence of events that results in contraction taking place, and then we'll ID some muscles and give you some muscle terms. So, contractile force in a single muscle fiber follows the sequence that we outlined earlier, right? Simple twitch to treppy to unfused tetanus to fused tetanus, okay? And then eventually we get to failure, right? The muscle will run out of energy, and the result is that the muscle will not be able to respond to a nerve impulse anymore, okay? Tonus is a continuous state of partial muscle contraction that is maintained as a result of an interaction between the spinal cord and the muscle itself. Okay, there are stretch receptors in the tendons and in the muscle fibers themselves that pick up whether or not the muscle is over or is overstretched, or whether the tendon is overstretched. If either of those happen, then you can damage the tendon or the muscle. And so what results from this is that um, if the receptors in the muscle sense overstretching, what will happen is that the muscle will respond by generating a contraction, right? So the receptors send information to the spinal cord, and then the spinal cord turns around and immediately sends a motor command back to the muscle without having to involve the brain, okay? And the same thing is true with a tendon, right? If a tendon gets overstretched, what will happen is that it'll send signals to the spinal cord to cause sets of muscles to contract and relax in such a way that you take the tension off the tendon so that it doesn't rupture. Okay, so as long as the connection between the muscle and the spinal cord is intact, tonus will be maintained. If the nerve that talks to the muscle is destroyed, then the muscle will very quickly degenerate. It'll undergo a change that we know as atrophy, where the muscle mass will decrease over time, and eventually the muscle is going to be replaced by scar tissue. Okay? The energy source for muscle contraction, the first immediate energy source is ATP. Okay, and if we take a scenario where you're engaging in sustained, powerful activity, okay, your ATP is going to be used up in a few seconds. Okay, there isn't that much that's stored in the muscle. The next maybe 10 to 15 seconds will be powered by the use of creatine phosphate producing ATP from ADP and phosphate. Okay, so it'll transfer its phosphate to ADP and make ATP. That'll only last 10 to 15 seconds, and then we'll go to a metabolic pathway called glycolysis, where the muscle cell will take sugar, either which is stored inside the muscle cell as glycogen granules, or which is coming from the blood supply, and it'll strip some of the energy out of that sugar and generate a product known as pyruvic acid. And then if the high intensity activity is maintained, what will happen is that the pyruvic acid will be converted to lactic acid, and the lactic acid will enter the bloodstream and eventually go to the liver. And then once the activity ends, the lactic acid will be sent back to the muscle, which will then strip the remaining energy from it in order to make enough ATP to pay its energy debt. Okay. The problem with using glycolysis this way is that it doesn't make very much energy. It only makes 2 ATP per glucose molecule, and that's not really enough to sustain intense activity for a long time. So eventually the activity stops. Okay. In the event that you're engaging in activity that's moderate activity, such as jogging or hiking, let's say, then you can use two other legs of metabolism that occur in the mitochondria of the cell, which are the Krebs cycle and the electron transport chain. What the Krebs cycle does is a series of enzymes that's in the matrix of the mitochondria, and they take pyruvate and they strip an acetyl group from it, and they use that to generate citric acid, the first molecule in the cycle. And then as the cycle proceeds from step to step and eventually gets back to the original first step, we generate some ATP directly, not very much, but we generate a lot of a molecule known as NAD and FADH2. Okay, and what happens then is that those molecules represent high energy intermediates that are going to then flow up to the electron transport chain, which is in the inner mitochondrial membrane, and they'll give up their high energy electrons to that chain. And as those electrons flow down the chain from one membrane carrier to another, these are essentially enzymes that are embedded in the inner membrane that are buddied up. Okay, as those electrons flow down that chain, they lose potential energy, but that energy is captured by the chain and is used to pump protons into the space between the outer and the inner mitochondrial membrane. And then in the final step of electron transport, those protons will eventually flow back into the matrix through a tunnel, which is an enzyme called ATP synthase. So as the protons go from where they're in high concentration to low concentration, that movement of protons is captured by ATP synthase and is used to make a lot of ATP, about 32 ATP per molecule of glucose that has its energy stripped from it. Okay, and that can only happen if there's oxygen around for the chain to run, because the oxygen sits at the end of the chain, receives those electrons, and then forms water, and then is let go. Okay, if the chain doesn't have oxygen attached to its end, then the chain won't run. Okay, the electrons won't flow. We won't steal the energy from them, and the result is that we won't pump any protons into the inner membrane space, and we won't be able to make any ATP. Okay, so in anaerobic situations or low oxygen situations, we can only run glycolysis. Okay, whereas in situations where we have oxygen around, we can run all three legs of metabolism. You can run the Krebs cycle without oxygen, but it really doesn't do you much good because you only get one ATP molecule per cycle, which would be 2 per glucose molecule, and then all that NADH and FADH2 just kind of sits around and does nothing. Okay, so that energy never gets utilized, never gets realized. Okay, so this is why we have to breathe oxygen in order to maintain normal activity in the body. Right? If we don't have it, we don't make enough ATP to live. Okay, keep in mind that in muscle cells, there are areas in the muscle cell where we store glycogen, which is a sugar polymer, which can act as a temporary energy store for the muscle. And there's also areas where we store oxygen bound to a protein called myoglobin. And that acts as a temporary oxygen store in the event that there are temporary reductions in blood flow to the muscle. But again, those aren't long-term solutions. Those get quickly exhausted when you're doing high-intensity activity. So this is why, for instance, you can only sprint maybe 50 yards or so, okay, but you can jog or hike many, many, many miles, right? Because in the jogging or hiking activity, the rate at which the blood brings the oxygen and the nutrients is equal or faster than the rate at which you're using them up. Whereas if you're sprinting, you're using up the oxygen and the nutrients way quicker than the blood supply can get them to you. Okay, so next we're going to talk a little bit about some muscle terminology. Okay, this applies to skeletal muscle. What you're looking at here is an illustration of the shoulder and the elbow joint. Okay, these are examples of freely movable joints, diarthroses, that permit a variety of movements. Okay, you can make almost any movement at the shoulder because of the nature of the bones that touch. Right, you've got a round head for the humerus and a shallow indentation, a socket for the head of the humerus, and so it can move in any direction. Okay, whereas down here at the elbow, you really have only one movement that's permitted, which is flexion and extension. Okay, you can either bend the elbow or you can straighten it out. All right. The origin is the muscle's attachment to immovable bone, while the insertion is the muscle's attachment to movable bone. Okay, and then the action is what happens when the muscle contracts. Okay, and then there will always be a muscle group that will do the opposite of that action. In this case, it's the triceps brachii, which is on the opposite side of the humerus. And that's to provide a little bit of a counterbalance to the action so that it's smoother and more coordinated. Okay? The prime mover in this case, where we're talking about elbow flexion, is going to be the biceps brachii. And then there are synergists that help. Okay? Other muscles that aid with you bending your elbow include the brachialis and the brachioradialis, which also cross the front of the elbow. Okay, and the tricep would be the antagonist. One of the things that occurs when we exercise muscle is that it gets bigger in response to tremendous use, right? when you put a greater load on the muscle's going to respond by making more muscle protein, and the result is that the muscle cells themselves are going to get thicker, and they'll generate more power. Okay, when you don't use the muscle, when you apply very little load to it, the opposite will happen. It'll make less protein, the diameter will become thinner, it'll generate less power, and that's a condition known as atrophy. Okay, atrophy can come from disuse or clipping the nerve leads to the muscle, either the nerves that go from the brain to the nerves that go to the muscle, or the nerves that go from the spinal cord to the muscle. If either one of those are damaged, then you're not going to get, you either won't have any signal get to the muscle or very few signals. And the result will be that the muscle will over time lose mass and lose power. Okay, and then senile atrophy is just what happens is our activity levels decline as we get older, and again, the less you use the muscles, the smaller they're going to become. Okay, contracture is just a condition in which scar tissue forms, and it freezes the muscle in a flexed position. Okay, and that could be often an end point for atrophy. Okay, so there's all kinds of ways that this denervation atrophy can happen. Trauma, disease, okay, a variety of conditions. All right. Okay. When we name skeletal muscles, we use a set of criteria that go under the acronym LADSNOR, L-A-D-S-N-O-R, which stands for location, action, direction of fibers, shape, number of origin and insertion, and then finally relative size. Not every muscle has each of these in its name because the names would be too long, but you can see from some of the examples here that components of the names are in different muscles, and they can give you a clue as to the muscle's location or action or attachment points. Okay, we have to learn these different terms that aren't in English, because the Greeks and the Romans got to the human body first, and as a result, they got the naming rights on everything. So we have to learn the way that they refer to stuff, and not simply use English equivalents. Okay, so this is an introduction to the muscular system. Okay, you want to watch and learn. For God's sakes, Petey, come on. Can you calm down?
System.
Hi, my name's Will. I'm the towel boy at the Neighborhood Health and Fitness Center. My duties include folding towels and also making sure towels get folded. They gave me a novelty t-shirt. It says Fold King. Sometimes I wear it to the park. And I'll tell you, working in a place like this, you can sure learn a lot about muscles. Huh? I mean, sure, there's 3 different types of muscles: cardiac, smooth, and skeletal. And skeletal is the only type you can see, but what you can see? Oh, pretty impressive. Hey, thanks, Rex. Fold King's on the job.
Section A, Introduction to Muscles.
There are 3 fundamental types of muscle tissue: cardiac, smooth, and skeletal. Cardiac muscle forms the walls of the heart and contracts to propel blood through the blood vessels of the body. Cardiac muscles are involuntary. Involuntary muscles are muscles we have no conscious control over. Cardiac muscles are striated, which means the muscle tissue has obvious stripes, or striations. We won't really get into cardiac muscle until we discuss the circulatory system in the anatomically correct world of anatomy, Part 2.
Smooth muscle forms the walls of hollow structures like the digestive tract. It's also responsible for changing the diameter of these tubes to move stuff like food through them. Smooth muscle is controlled by the autonomic nervous system, which we'll talk about later. Basically, this means that smooth muscle works without any conscious help from us. It's on autopilot.
Smooth muscle cells are unstriated. That means they don't have the stripes that cardiac and skeletal muscles have. But like cardiac muscles, smooth muscles are involuntary. We can't control them consciously.
Section B, Skeletal Muscles.
Skeletal skeletal muscles, the final division, are typically attached to the skeletal system, hence the clever name, skeletal muscles. These muscles are the most plentiful and their names are hard to memorize, so we're going to focus on them for a while.
The skeletal muscles are also responsible for body movements and facial expressions. Throwing balls, running from the police, frowning in disgust, all these things are the bread and butter of skeletal muscles. Skeletal muscle cells are elongated, striated, and under voluntary control.
So when you think skeletal muscles, think striated and voluntary.
Apart from movement, skeletal muscles have a number of other responsibilities. Skeletal muscles help you stand. They maintain posture by resisting the pull of gravity.
Nothing can resist the downward pull of gravity. Just watch. Hup! It's impossible, I tell you. Impossible!
I appreciate and understand your concern, insane man, but the skeletal muscles actually can do it. They can also adjust themselves to stabilize joints and even generate heat during muscle activity.
Heat? By God, where can I get me some skeletal muscles?
You already have over 600 of them. Isn't that wonderful?
But there is one catch. You see, skeletal muscles are named using 7 different naming criteria. Within each muscle's name, there are certain descriptions that characterize the muscle. These naming criteria are location, shape, relative size, direction of fibers, number of origins, origin and insertion, and lastly, action. Knowing these naming criteria will help you identify muscles more easily on an exam, or help you understand more about individual muscles when you hear their names.
Location refers to the bone or bones that are directly associated with a muscle. For instance, the temporalis and frontalis muscles are named for the cranial bones underneath them. The temporalis is above the temporal bone, and the frontalis is above the frontal bones. Piece of cake.
Shape describes a muscle's approximate shape. For example, the deltoid muscle is triangular. In case you don't know, delta is a Greek symbol shaped like a triangle. And the trapezius, another muscle, is in the shape of a trapezoid. Simple, isn't it?
Another way to classify muscles is through relative size.
For example, the terms maximus and major refer to the largest group of muscles. On the other side of the coin, the terms minimus and minor refer to the smallest group of muscles. Longus and brevis are 2 other muscle terms that describe size. The term longus refers to the longest muscle in a muscle section, and the term brevis describes the shortest.
You get the point? Muscles can be classified by their size, too. Another way to classify a muscle is by its direction of fibers.
The direction of fibers describes the orientation of muscles relative to the long axis of the body. The long axis of the body runs from head to toe, so muscles can be rectus, meaning straight. In this case, they're flush with the long axis. Muscles can be transversus, meaning across. This means they're perpendicular to the long axis of the body. Or, muscles can be oblique, meaning they're oriented at an angle to the long axis. It's as simple as that. Rectus straight, transversus across, oblique, angle.
The number of origins refers to the number of attachments a muscle has to bone via tendons.
For example, the biceps have 2 attachments to bone in the forearm, the triceps have 3 attachments, and the quadriceps 4 attachments.
Next up, origin and insertion.
The origin and insertion of a muscle describes its attachment to bones. Origin describes a muscle's attachment to immovable bone, and insertion describes its attachment to movable bone. Take the sternocleidomastoid muscle. This muscle originates from the sternum and clavicle. In simple terms, that's the beginning of the muscle. But the sternocleidomastoid eventually inserts itself on a part of the temporal bone called the mastoid process. We get sterno from sternum and cleido from clavicle. Then we get mastoid from mastoid process.
Put it all together? Sternocleidomastoid. It's like a puzzle for science lovers.
The next muscle classification is action, which indicates the type of movement a muscle creates. For example, the flexor muscle decreases the angle between bones, like when you're lifting up a dumbbell. The flexor flexes. The extensor increases the angle between 2 bones, like when you're bringing that dumbbell down. The extensor extends.
And that's the 7 criteria for naming muscles: location, shape, relative size, direction of fibers, number of origins, origin and insertion and action. Now, not all muscles use these 7 criteria in their names. They'd be way too long. But there are some muscles that are described using a number of them. So it's a good idea for you to be familiar with them all. A good way to remember all these ways to classify muscles is by using the phrase lad snore. You see, each letter in this word is the beginning letter of a term used to describe muscle orientation and location. Commit it to your memory, lad snore. A little English boy who can't sleep quietly.
I wish I could stop snoring.
Hey, 'tis true. The lads snore.
I'm also an narcoleptic.
Being familiar with all 7 muscle naming criteria does make it easier to identify the skeletal muscles. So, with that in mind, let's take a long, hard look at the skeletal muscles.
The skeletal muscle.
Considering most of us have no exposure to muscles outside of the times Popeye the Sailor Man made battleships appear in his upper arm, this is going to be a challenging task. Just never lose sight of the fact that you can rewind and review whenever you feel the need to.
But what if my remote has been
smashed by some sort of hard blood instrument? Well, then I guess you'll have to pay extra close attention. But that won't be hard, because we've got renowned educator and international megastar Slim Goodbody to help us learn about muscles. Why don't you come on out, Slim?
Hello!
Hey! All right! Are you ready to learn?
Oh, yeah, I guess so.
I wasn't talking to you, but that's okay. Let's learn!
Muscles of the head.
Let's start off with the muscles of the head. Head muscles are usually broken up into 2 groups, those that manipulate our facial expressions and those that help us chew and move our tongue. The muscles that control facial expressions are those of the scalp and face. These muscles are unique because they're the only skeletal muscles that are attached to skin and other muscles as well as bone. And Slim Goodbody has kindly agreed to help us demonstrate the use of tongue and facial muscles by allowing me to tie this rope to his tongue and drag him about the room.
I never agreed to that.
Oh, come on, Slim, do it for the kids.
I'm not going to let you tie a rope around my tongue and drag me around the room.
The main muscle of the scalp is the epicranius, which is made up of the frontalis and the occipitalis. Important muscles of the face are the orbicularis oculi, zygomaticus, risorius, orbicularis oris, and the buccinator. It's easy to remember the muscles containing the prefix orbit because it should remind you of the orbitals in the cranium.
The 3 important muscle pairs connected with mastication or chewing are the masseter, temporalis, and pterygoids. The muscles that move the tongue when we speak and eat are the intrinsic muscles. The intrinsic muscles change the shape of the tongue itself. The extrinsic muscles are also important to the tongue because they anchor and move the tongue around inside of the mouth.
Now look, I'll just make it a soft knot.
No, listen, you tie the rope around your tongue, huh?
I'm not the guy with the suit. Now let's look at the muscles of the anterior neck and throat. These muscles help us swallow. Our friend Slim Goodbody has agreed to demonstrate the use of the throat muscles by swallowing a tennis ball with a nail sticking out of it.
What, a normal tennis ball isn't enough? Slim, please.
The muscles of the anterior neck and throat include a bunch of muscles that attach to the hyoid bone. These include the suprahyoid muscles and the infrahyoid muscles. Behind all these muscles that move the hyoid and voice box is the pharyngeal constrictor muscle of the pharynx. This muscle helps us swallow.
No.
Do it.
No.
Do it.
No.
Do it.
There's a nail sticking out of it.
Other muscles of the neck are responsible for movement of the head and body trunk. Slim Goodbody will demonstrate the muscular movement of the head by driving this car...
Hey, I can do that.
...straight into a reinforced steel wall.
Hey!
The muscles responsible for moving the head and neck are the sternocleidomastoid, scalenes, splenius, and semispinalis. The trapezius muscles of the back also help move the neck and head, but we'll cover them in more detail later on. The muscles that help move the trunk of the body are the erector spinae, the semispinalis, and the quadratus lumborum.
Look, whoever nicknamed you Slim Stunt Body didn't know what he was talking about.
No one named me that.
Ooh, pinched a nerve. Oh, shit. The deep muscles of the thorax help us breathe, plain and simple. Now let's watch Slim Goodbody inhale a tank of water.
You're insane.
The deep muscles of the thorax are easy to remember. They're located around the thoracic cavity. They are the external intercostals, the internal intercostals, and the diaphragm.
The water's been purified.
I don't care.
Now, most people believe that the superficial muscles of the thorax are the same as the deep thoracic muscles, except that they date cheerleaders and enjoy teen magazines. Now, this is not true. The superficial muscles of the thorax actually act on the scapula to create arm movement, like pushing or punching. Watch Slim Goodbody as he uses his superficial thorax muscles to fight this man-sized boxing cow.
Do you come up with things like this yourself?
The superficial muscles of the thorax are the pectoralis major, the pectoralis minor, the serratus anterior, the subclavius, the trapezius, the rhomboids, and the levator scapulae.
Will you stop it? The muscles of the abdominal wall control the movement of the body's torso and provide protection for internal organs. When the abdominal muscles contract, the pressure within the abdomen increases. Well, this helps us to sneeze, vomit, cough, scream, give birth, burp, and blow our noses. Hello.
Don't even think about it.
The muscles of the abdominal wall are the rectus abdominis, the external oblique, internal oblique, and the transversus abdominis.
I wasn't gonna ask you to vomit. Much. Next up are the muscles of the pectoral girdle. The muscles of the pectoral girdle move the arm by directly acting on the humerus and help with actions like swimming, hammering, and rowing. Slim Goodbody will demonstrate the use of these muscles by operating this rowing machine.
That's it.
That's it.
No piranha, no head trauma.
No.
All right, we're finally getting someplace.
The muscles of the pectoral girdle include the pectoralis major, the latissimus dorsi, the deltoid, and the teres major. Also included in the group of pectoral girdle muscles are the rotator cuff muscles, which include the teres minor, the subcapularis, the supraspinatus, and the infraspinatus.
Oh, that was quite a workout.
I laced the handles of the rowing machine with an hallucinogenic agent. No, really, I did.
I'm calling my lawyer.
The muscles of the arm cross the elbow joint and insert on the forearm in order to move it. They are the triceps brachii, the biceps brachii, the brachialis of the arm, and brachioradialis of the forearm.
The superficial muscles of the forearm are the pronator teres, the flexor carpi radialis, the plumaris longus, the flexor carpi ulnaris, and the flexor digitorum superficialis. The deep muscles of the forearm include the supinator, the abductor pollicis longus, the extensor pollicis longus, the extensor pollicis brevis, the extensor carpi radialis, the extensor digitorum, and the extensor carpi ulnaris.
The muscles of the hip are the muscles responsible for moving the thigh. I will now demonstrate the use of the hip muscles by cautiously walking away from Slim Goodbody, who's slowly creeping up on me.
Hey, muscle boy, why don't we have a little chat?
The muscles of the hip include the iliopsoas, the sartorius, the adductor magnus, the adductor longus, the adductor brevis, the gracilis, the gluteus maximus, the gluteus medius, and the gluteus minimus.
Okay, now I'm gonna let you go. But first, we're gonna set some ground rules, okay?
Okay.
Now, the first thing, I want to be sure.
The muscles of the thigh move the leg. Now remember, the thigh and the leg are different. The thigh is superior to the leg. I will now demonstrate the use of these muscles by running from the madman who's trying to kill me.
I should have done the gig in Vegas.
The muscles of the thigh include two major groups. These groups are the quadriceps, which extend the leg, and the hamstrings, which flex the leg. The four muscles in the quadriceps group are the rectus femoris, vastus lateralis, medialis, and intermedius. The hamstrings are composed of the biceps femoris, the semitendinosus, and the semimembranosus.
The muscles of the leg move the ankles and toes. Normally, I would demonstrate these muscles, but if I move a muscle, Slim Goodbody will, what was that, Slim?
Turn your head into a salad bowl.
That's it.
The muscles of the leg include the tibialis anterior, the extensor digitorum longus, the peroneus, the gastrocnemius, and the soleus. Also included are the deep muscles of the leg. These are the flexor digitorum longus, the popliteus, the flexor hallucis longus, and the tibialis posterior.
Before we settle our differences man to man, how about an anatomical fun fact?
And now, an anatomical fact with the renowned yet slightly annoyed Slim Goodbody.
Did you know that the hamstrings got their names when butchers would hang up large pig tendons for smoking and curing? Are we learning or what?
Oh, yeah. Can I just give one more helpful tip for naming muscles? Remember, for the most part, each muscle system is responsible for moving the structure below it. So, the muscles of the thigh move the leg, the muscles of the arm move the forearm, etc. And that's the muscular system. Simple, isn't it? Oh, and don't forget, you can always rewind the tape and review the names and locations of all these muscles so they stick in your head. Or, you can rewind the tape right now so that I don't get beaten up.
Tying rebar is hard, physical work. It's also an example of a job that involves repetitive use of the wrist. Use that can cause problems such as carpal tunnel syndrome. Carpal tunnel syndrome is a condition that interferes with the use of the hand. It's caused when too much pressure is put on the nerve that runs through the wrist. To understand carpal tunnel syndrome, it helps to understand the anatomy of the wrist. The wrist contains tendons and nerves inside a narrow tunnel. This narrow tunnel, the carpal tunnel, has a fixed diameter. In carpal tunnel syndrome, symptoms occur when there is pressure on the median nerve. This pressure on the nerve in the narrow tunnel of ligaments and bones causes the symptoms. Some of the symptoms of carpal tunnel syndrome include numbness, tingling, and pins and needles. For more information on carpal tunnel syndrome, visit WorksafeBC.com.
Okay, well, this brings us to the end of the Chapter 9 podcast. Again, if you have any questions, make sure and contact me. I'll be happy to help you out. Again, email is my preferred method. I'll get back to you within a day, and I will see everybody in the next podcast. I thank you for listening.